Okay, welcome everybody. Today we're going to have Steven Sanchez Perlaza, a Colombian guy, but now he's going to do his PhD master, at Chile in the Arturo Prat University. He's going to speak about on black hole mass. Okay, he hid the title, but it was almost like that. Yes, on the calculation of black hole mass. So sorry. So go ahead, Steven.
Okay. First, thank you to the organize, Lucas, Matias, Mayrin, and Martin probably is other organizer. Thank you so much for this opportunity. Okay. Secondly, I want to begin with the title of this presentation. I think this presentation, the key idea there is inside of this title. Okay. Begin with the on calculation. Calculation means we get some number, right? We compute some things, we have formulas, and we get some number of these formulas. After we have mass. In the school, we learn that mass is like the quantity to measure matter, right? We have matter in some volume, and we have mass to measure this quantity, the number of atoms and something like that. Okay, but as I said, we have mass inside a box or some volume. This volume represents space, and we have space and we have mass, but also we have some dynamical behavior for this matter. And we describe this dynamical behavior using time, right? We have some clock, and this clock is useful to understand how mass changes inside of this box. Okay, we could think about in this picture. You have particles inside a box in a box and something like that, and we study the dynamical behavior of this matter. Okay, uh, in the last century, Einstein broke down this idea. Sorry. Um, he studied or he created a new idea about these three things: about time, about the space, and matter and energy. The idea was we don't have space and time, we have space-time. We have a mixture between space and time. Um, this is the first relation. We have this space-time, and after we have obviously this grip. You describe the space-time, but also the mass is not just an actor in a scenario. It's an active actor. The mass curve, this graph, the space-time graph, the mass, this mass describe uh, some path in this space, but it's as a consequence of this curvature of this graph, right? Uh, the conclusion is the space-time is a dynamical object, and this dynamical object have a particular relation with the mass and energy that we have in this group. Einstein described this relation with the Einstein field equation, with this equation, geometrical equations, where we have in the left side geometrical structure who describe how this grip, how the space-time is modified or is curved by in the presence of energy or matter. And the right side we have matter, how the matter move in through this space-time curve, right? Curve space-time. And the third, the final word or concept is black hole. In normal life, we could think about holes. If you have some t-shirt, you have some hole in this t-shirt. You could say this hole is a two-dimensional hole, right? And some characteristic of this hole, there are three characteristics who define this hole. We have some interior, some boundary, and some complementary space. The interior is all the points, the set of points that are in the in around of or in the interior of the boundary of this space, right? We have the interior points, like in the center of the circle, we have the interior of the circle, and the boundary is the circumference, right? The complementary space is other things that is with in the exterior of this of this boundary, right? And obviously, we could think about a three-dimensional hole. You could think about a bubble, sorry, and this is an example of three-dimensional hole. We have the same thing. We have interior boundary, a complementary space. We have this surface, the interior of this bubble. We have the surface of this bubble, and we have all the universe uh, of the universe of this around this bubble. Uh, why what is the special idea of black holes? That is in the name we have the special idea. We have the name is black. We have the first noun or adjective uh, of these holes, and this is a consequence of other history that Einstein um, told us in the last century. Uh, the other story is we have a limit to information propagation of information in the vacuum. This limit is the speed of light. Okay, we have this limit, and if we have some holes in the space-time as a solution of these equations, we have these holes, but these holes swallow everything in the universe. If this is the life and something on everything, matter and energy and something like that. Okay, if black holes swallow everything, even life, we don't have we just this black word black to describe its color, right? And this is the idea of black holes. In this picture, we have some idea of black holes. We have a black dark bubble or black bubble. We have some accretional disk as a consequence of these black holes swallow some star. In the 90s, 70s, Beckens and Hawking learned or studied these black holes, and they found these black holes are very very complex monsters. It is not just a bubble, a dark bubble. There is some statistical physics behavior. Um, um, this this as a consequence of that, Hawking and Bekenstein describe a new ideas around these black holes. What ideas? Which ideas? Their objects have temperature and entropy. We have a microstates who describe the entropy inside of the surface. Surface that means the um, events horizon of the black holes. We have some thermodynamics laws of thermodynamics for these objects. In this point, we have the first law of thermodynamics. We have a relation between mass, temperature, and entropy. We have a zero law, a first law, a second law of thermodynamics for these objects, for black holes. What's the importance of that? What's the importance of that? All the physicists study these black holes. All the physicists are happy to to study first law or these thermodynamics relations, but they always assume that this first law is satisfied. This implies that we don't have to ask for how compute the mass. We just have method to study the temperature, the entropy, and we just assume this equivalence is right, and we obtain the mass before we compute time plus the variation of entropy, right? Okay, it's pretty cool, it's good, works, but in the last century, in 1990, in the 70s, in the 2000s, um, close to 2000s, uh, Juan Maldacena, Ed Witten, others study or discover a duality between some gravitational theory, quantum gravitational theory, um, in the interior, on some in the interior, or in some of some gravitational space. Um, this relation describes this theory, a duality between this theory and his boundary space as a CFT theory. We have in this way we have a duality between some gravitational theory and some non-gravitational theory. Okay, it's cool. It's pretty awesome, but if you study black holes in the interior of this space-time, and we do a black hole tuning, we have problems because we we have to prove this black hole tuning is right. We could create black holes to understand CFTs, but to we need to taste that these black holes are satisfy, for example, the first law. But as you know, if we know that this equivalence is right, we have to prove by the first principles. We have to prove this equivalence from the left and right to the right side, and from the right side to the left side. Okay, we just have one way. We don't have both ways because, that I said, all the physicists assume that we have methods to study temperature and entropy and no more. When the physicists figure out or figure out about this idea of the equivalence, physicists get in troubles because they compute the mass, or in particular, in general, conservative charges in general theories, in particular in Einstein's physics equations, are very hard. It's a hard work, and depends hardly of the depends hardly of the geometrical topics on topological behaviors of topological behaviors or asymptotical behaviors of each space-time. This is a complicated problem, and actually currently it's a huge a huge campus or research way to understand better uh, general relativity stuff, right? Okay, in this way we study three methods to compute conservative charges, but we study in particular how compute mass. The first method is the ADM method. This method was created by Arnold Desermeisner. It was created in 1962. Is the simplest method. This method begins with this. Okay, we have general relativity. We have four 3 plus 1 dimensions. Okay, we decompose this 4-dimension space-time in 3 plus 1 dimension. We have some, obviously we know, in general relativity, we don't have a special arrow of time. We don't have a special coordinate system or coordinate frame. In this point, we choose a specific time arrow. And with this special direction of time, we choose a foliation of or this space-time, 4-dimensional space-time, by acornal, smooth, and complete surface. This means Cauchy slices. We have Cauchy slices, and we, as an embedding of this background space, four-dimensional background space-time, right? That's it. We have some 3-dimensional slices through one direction of time, a specific one direction of time, right? If we decompose the space-time in this way, we could ask for how describe the dynamics or of this of each point in this space-time. And we describe this dynamical behavior with this 4 vector. These 4 vector are decomposed into new variables. The first is is named shift variable, and the second one is the lapse variable, who scale the normal vector. This normal vector is a normal vector of each point to each point in this Cauchy slice. And with this vector, with this composition, we could describe all the dynamics in this 3 plus 1 decomposition. Also, we have an embedding surface. We have a intrinsic metric and background metric. Okay, we have other variable. We have intrinsic metric as a metric inside of each Cauchy slices. We have G like the background metric. Okay, these 3 variables names are ADM variables: the shift, the lapse, and intrinsic metric. And all these 3 variables describe all the behavior, all the dynamical behavior in this 4-dimensional space-time, decomposed in 3 plus 1. Obviously, if we have an exterior background, we have an exterior place, we could choose some normal vector, and we could move this normal vector through these Cauchy slices, and we could measure how this normal vector change, and how this normal vector change told us about how this Cauchy slice is curved, right? If you do this for each point in this Cauchy slice, we could get some new tensor. This tensor names is the string-set curvature tensor. Is given by the ADM variables, right? Obviously, if you have this idea of curvature, you could get the complete Ricci scalar tensor, 4-dimensional. You could decompose this 4-dimensional Ricci tensor as a projection of this Cauchy slice and other things. Given by the stereo curvature tensor that way. Okay, we have this delta. In this delta, we have some combination of normal vectors and covariant derivatives, and in a few minutes, this combination will be important. But okay, this is the decomposition of the four-dimensional scalar, rich scalar. Okay.
Sorry, Steven, a short
Yeah.
question. The
Okay.
indices RB,
Okay,
which value
you're right.
takes? Uh,
Yes, you're right. You're right. The Greek letters talk about the complete space, and Latin letter talk about the Cauchy slices coordinates. Okay. Sorry. You're
so how many? mu goes from 1 to 4, and A, B. How many
right.
Cauchy slices you have? How is that
No, no,
work?
no. The Latin indices we are one, two, three. The Greek letters are from 0 to 3. Uh-huh.
Okay, 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 okay.
Okay. Cool.
Yes.
Okay. Okay. In this point, okay, we have all the things to talk about uh, a gravitational action. Why? Because we have the composition of four dimensional Ricci scalar tensor. Okay, we have a piece in this picture. We have a piece of space-time, like a piece of cave, and we have three surfaces. We have the top uh, surface, the bottom surface, and we have the boundary surface, right? Okay. In this point, we could ask what is the general idea, the typical idea of gravitational action, and we obviously have the Einstein-Hilbert action, the boundary action, the Gibbons-Hawking-York term, and the non-dynamical term that is like a constant term who banish all the divergences that we could get in these two terms, right? Okay, we have the normal idea of that. We had four-dimensional rich scalar tensor, and we have difference between a subtraction between scalar stringent curvature in, 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 in this way, okay? Okay, we have the explicit expression for this four-dimensional rich scalar tensor, and we could divide all the expression in thinking about this piece of space-time with the 3+1 decomposition, and also with the four-dimensional Ricci scalar decomposition in 3+1. Okay. Notice that in this point, we don't have a capital K letter, we have kappa, because in this point, we just study each Cauchy slices, and in the interior, we study, in the interior integral, we study each Cauchy slices, and the exterior integral describe how an integration and time integration of each Cauchy slice, right? In this point, the kappa letter is the scalar extrinsic curvature in the boundary of each Cauchy slice. Okay, when we have the capital K letter, we have the extrinsic curvature scalar in each point of these Cauchy slices. In this point, in the case of kappa, we have just the scalar extrinsic curvature in the boundary, at the boundary, sorry, at the boundary of each Cauchy slice. Okay. Okay, if we study this new decomposition, we could get some Lagrangian densities, volume Lagrangian densities, or boundary Lagrangian densities. What is this important? Why is important? Because we could ask uh, ask for general relativity Hamiltonian. If we have some Lagrangian density, we could construct or create a Hamiltonian, a Hamiltonian density. Okay. In this method, ADM method, we realized that we just have one dynamical variable. This dynamical variable is the intrinsic metric, and this intrinsic metric give us a conjugate moment. This conjugate moment explicitly is in this way given by the ADM variables. With this conjugate momenta, we have the volume Hamiltonian and boundary Hamiltonian density. If we put together all together, we could get a general Hamiltonian. This Hamiltonian, we could compute explicitly each part, and we get some part volume part and some boundary part. Especially in general relativity, when we study Hamiltonian, the general relativity Hamiltonian, we get that the volume Hamiltonian, the interior Hamiltonian vanishes, is zero. This volume Hamiltonian volume is zero, and we just have the boundary Hamiltonian. Okay, in this point, Hamiltonian is very useful because it's a little simple, but we wanna get some information about this Hamiltonian. In particular, if we want to learn some about this Hamiltonian, we could assume or suppose some ideas. In particular, we suppose that our space-time is asymptotically flat space. Why? Because we could understand the mass of this space-time. What is the intuition of that? We could imagine some Cauchy slice. Also, you could imagine some Cauchy slice. If you have some domain in the interior, you have in the interior some curved space. You could have some black or something like that. And obviously, that if you remember that all that I said, if you think about the dynamical behavior of each point between one Cauchy slide and another, this T vector is not parallel with this capital letter T vector that means or represent, sorry, the evolution, how the Cauchy slices evolve, right? Okay, it's not parallel. If you go away this domain, you could, if you have asymptotically flat space, you get some Lorentz frames, Lorentzian frame of reference. This means you have a parallel vector who describes the dynamical behavior of each point, parallel to this temporal evolution capital T vector. This means if you are in this point in this flat space, asymptotic flat space, you feel like you don't have a spatial move. You just move in through the time, right? When you what is the consequence of this pictorial idea? The consequence is, if you remember, what's the explicit form for this T vector? If you choose this parallel vector with the capital T vector, if you have to get this parallel vectors, you should have this shift variable equals to 0 and this lapse variable equals to 1. When you choose this specific configuration for T vector, you have parallel. You have a Lorentz frame of reference, right, in the boundary of this spacetime. obviously, this works to compute the black hole, the charged black hole mass. How? Because oh, we define the ADM mass as the limit, uh, or the limit to infinity of, I mean, when you at in the boundary of this space-time of this difference between this kappa and the kappa zero. What is the intuition of this uh, equation? Okay, you have you have a kappa minus kappa zero. Kappa represents space-time with something, with a black hole, with something, with matter in its interior or energy. And kappa zero is space-time, a vacuum space-time, right? And you could think about that. For example, if you have a bed sheet, and you have this bed sheet, and you take this bed sheet by the heat, but is boundary, someone covers your eyes, this guy tell you about, okay, in this moment you feel some pull, you feel some pull through by the interior of this bed sheet, but obviously uh, this guy could be put some inside of this bed sheet, in the center of the bed sheet, and you feel that this um, sheet are stretching, right? Like you feel some pull, like you feel some gravitational pull in the from the interior of this piece of sheet, right? Um, okay, this is the same idea. We have in the interior, we have this intrinsic metric, the black hole structure black hole metric, and we have flat coordinates in the asymptotic flat space in the boundary, right? And we could compute the um, extrinsic scalar extrinsic Hilbert tensor at the boundary in both in for the structural metric and the vacuum metric, and we could compute the ADM mass, and we get the black hole, the structural black hole mass. Pretty good.
Sorry, Steven,
For
remind me, what is the measure here? I mean, you are interacting with the square root of sigma. Sigma,
sigma is the the metric in the interior, or the in the at the boundary of each Cauchy slice. Okay, we have,
okay,
yes, okay, we have this metric. This metric is the metric induced in each Cauchy slice. Okay.
okay, um, okay, great. Because then you say that the intrinsic metric was gamma, and so I got confused.
Okay, okay.
Okay,
I try to explain that. Okay, we have G. This is the metric in all the space-time, the four-dimensional space-time. Okay.
mhm,
Gamma is the metric, the intrinsic metric for each Cauchy slice. H is the metric of the boundary of this piece of gravity space-time. But if you localize in the boundary of each Cauchy slice, no, nor or this wall, no, it's just for this line, this curve, you have sigma. Okay.
okay, okay. Thank you.
Okay, okay, this method works. It's pretty awesome. We could compute the black holes, the first black hole mass. Pretty good. But we have problems because the where is the, where which are the key ideas of this method? We have globally hyperbolic, probably I forget. define what is hyperbolic space. Hyperbolic space is just a space who are foliated but cauchy-sliced, okay? And okay, we have a globally hyperbolic space, and we need a flat asymptotic flat space. It's pretty, this is the key idea of this method, but we know that normally the spacetimes are not globally hyperbolic as ADS anti de Sitter space. We don't have hyperbolic space in this case. And also, normally the spacetimes are not flat asymptotic flat space, right? It's a little boring, this uh, asymptotic behavior. Okay, it's not. We need a more general idea, a more general method. Okay, in this way, the ADT method about desert taking create or discover a new method to study conservative charges in Einstein field equation in Hilbert actions types of theory of gravitational theories. This method was created by in the 1982. After in the 2000s, about desert and taking create a more generalized ADT method for more general theories like um, high curvature theories, not just Einstein field equations. But in this point, we study just Einstein field equation. We apply this method to study solution of Einstein field equation. Okay. In this method, we discuss more general spacetime. We don't need spacetime global hyperbolic spacetime. We could study other spacetimes as a consequence of this cosmological constant. As we know, this cosmological constant give us a topological asymptotic topological behavior, a different asymptotic topological behaviors. If we have this zero, this cosmological constant equals zero, we have flat asymptotic flat space. But if we have positive or negative cosmological constant, we have de Sitter or anti de Sitter space. Okay, it's more general than ADM method. Other thing is we don't have we don't okay what this is more general. We don't have to global hyperbolic globality or in this space time. It's a more general method. How works? We use a background metric and we perturb this background metric by some perturbation metric. We just need this perturbation metric to vanish at the boundary space-time boundary. This perturbation metric could be small or big. I don't know. It's not important. It's just the importance of this metric is just that this perturbation metric to vanish at the space-time boundary. And we perturb this background metric and we construct some solution, for example, a black hole solution. To begin, we create this. We have the Einstein field equation, for example, at the vacuum equations, and we perturb this background metric. We decompose each this Einstein field equation in different orders in H, right? The zero order, we obviously is vanished because we work in the vacuum. The linear order and second, third, fourth order in H. We after we decompose this Einstein equation, we put in the left side the linearized equation, and the right side we put all the second and higher orders in H, right? we name this second and higher order in H as a tensor density, as a, right, like a high energy momentum tensor. Obviously, we could study using the Bianchi identities. We could study this equation, and we find this equation is covariant conservative. It's covariant conservative, but it's not useful because we know covariant conservative is not useful to find conservative charge because it's local. We need a global conservation quantity, conservative quantity, and this is the reason that we need to figure out think about something about in this equation. And we use the background killing vectors. We use background killing vectors, and we contract the energy momentum tensor with this background killing vector, and we prove this contraction is conservative, globally conservative. We could define spatial integral and define as a killing energy in this way. We could also we could rewrite this contraption by these two new tensor, capital K tensor and capital X tensor, who are right in terms of H. You could see capital X is in terms of K, capital K, but capital K is given by H. Right? If we have this equality, we could rewrite the killing energy, and we could get this expression in terms of capital K, and obviously this K is given by H. This is an expression of killing energy in terms of the perturbation metric. Okay, cool. This is the ADT method, but we use this method to compute the DS Schwarzschild metric or Schwarzschild. Okay, I write explicitly this killing energy in terms of this perturbation metric, some temporal killing from this ether space. With this explicit expression, we in this moment we just need the explicit DS de Sitter metric. De Sitter metric. In particular, we use the flat slicing coordinates, and we use the DS Schwarzschild black hole. We subtract both of this metric, and we get the perturbation metric. Right? Obviously, we have we need the temporal killing of the background of the sitter. In this point, we use this Taylor series to satisfy this perturbation method to vanish at the space-time boundary. If we use this Taylor series, we rewrite all the components of this metric in this way, right? Obviously, we have R0 as the Sitter Schwarzschild radius, and R is a general generical vector R, sorry, in this space. And we also get the DS, the Sitter Schwarzschild black hole mass. Okay, we could prove these ideas just substituting this to put inside this explicit components of this perturbation matrix. We could put inside of this expression, and we get the Sitter Schwarzschild black hole mass. Okay. Sorry. Finally, we have some conclusion. Okay, this method is more general than ADM method, but we had other problems. For example, and I forget to say that, but sorry. Uh, this metric that we use, this background metric in the ADT method, this G bar metric should be a vacuum equation solution. We need vacuum solutions, vacuum equations, and with this vacuum equation, we get this background metric. It's a problematic stuff because we limited, we have limits to which metric we could choose, right? Secondly, we have this, we need a temporal killing. Obviously, we have this perturbation metric. And this means, obviously, we need the black hole metric to study all this ADT method or to apply this method. And so it's a little, we have a little limits with this method. Okay, what happened with backgrounds, general backgrounds, not just backgrounds who are a solution of background equation. Okay, we have to learn a third method, the most general method. This is the quasi-local method. This method was created or discovered by King Kulkarni G in 2013. This method is the most general method to compute, it's the most general method to compute conservative charges in a general theory of gravity. There is a lot of other methods, general methods, but this is in this talk I explain about this method. This method need some general theory of covariant gravity in this d dimension. You could have derivatives, covariant derivatives, or reaches, right? It's just we need a general theory of covariant gravity. And after that, we could think about the variation of this option, general option, with respect of the metric. Also, we could think about the variation of the metric of the variation of the Lagrangian by diffeomorphism, by diffeos, right? Diffeomorphism. With this variation with respect to some diffeo, and we're using the Bianchi identities, we could get off-shelf nether cover. We work off-shelf. In this moment, we work off-shelf, and we get this result. This on-shelf current, nether current, is globally conserved. Okay. In this moment, we
Yeah, can you go back to the previous slide? Yeah, this last thing you wrote is like the current of the isometries of a fit set spacetime or something like that.
Exactly.
Oh, okay.
Okay. Yes. Imagine obviously you have some diffeo, and you learn how what is the quantity that you get as you that is conserved by this diffeo, right? This is the quantity. Yes. Okay.
But this will depend of the boundary conditions you put in the Lagrangian.
Exactly. Yes.
So
You're right.
So I don't know where, but here you should have something like the extrinsic curvature or something like that.
EPA. Yeah. Yes. Yeah. Right. But in fact, okay, we discussed probably at the end because we have, if you remember, in the ADM method we studied this. Okay, Brown your action something like that. But we have other not dynamical action in this point because we have divergences in the at the boundary, something like that. But uh, this method doesn't need these contra terms because the own construction of this method doesn't depend of the surface we study these conservative quantities. Okay, some slices in some slices we will talk about that. Okay, yes, we use this nether current, and obviously if we have some nether current, we have a potential associated with this current. This current, this potential, with this potential, we could think what happen if we variate something, the background metric, the generical background metric. We just perturb some a little this background generical background metric, and we fix the contravariant components of killing vectors. What happened with this potential? Well, okay, the explicit form of this variation is this. And also, we could remember the ADT method, and we work with this method of shell. We in the last method we also we just work in on shell. We work on shell, right? And obviously our net or ADT current is just this point. This is this term, sorry, this term. But in this point, we study off-shell ADT current, and we have this term, and we have other terms. Obviously, if we have some ADT current, we have associated with this current a ADT potential. This ADT potential could be rewrite well. Okay, it's pretty interesting. We have two terms that are equal in the off-shell ADT potential and off-shell Noether potential. Okay. King Carnegie used this in this point. They used this idea to get together the off-shell Noether potential and off-shell ADT potential. They are related. Okay, they are related, and we have this expression for the ADT potential in terms of the linearized off-shell Noether potential. Beautiful. King Carnegie used the Glenn Barnes paper, to study this specific expression. Two things that that King Carnegie used for study this expression. First, we could notice this is a 2 minus d closed differential form. This means that we don't have to use the boundary to understand what happened in the interior of this space-time. We just use a specific surface with a compact surface with a radio with a radio bigger than which radio is bigger than the black hole radio, right? And with this in this surface, we could define all of these tensors, right? This is the idea of quasi-local. We don't have a global global idea. We don't have a volume and a global integration. We just have, and obviously we don't talk about local set of points. We just have a extended set of points, but a finite set of points. We have a surface. And this surface not depends of the radius of the surface. We just need the surface are a quasi a 2 minus d dimensional surface. Okay. And the second thing is, imagine you are in this boundary, in this surface. You could put a label. Imagine you have a label, and this label allow us to turn off or turn on all the things that are in the interior of this surface. For example, a black hole. You have a black hole, and you have a label, and you turn off the label. You turn off you don't have black hole. But if you turn on, you have a black hole. Obviously, if you have a parameterized path, you have some smooth path where you could turn on or turn off this black hole in the interior of this surface. With these two ideas from Glenn Barnish, King Kulkarniji defined the quasi-local quantity energy, the quasi-local energy. And with this idea, you could see that you don't have to study the space-time at the boundary. You don't have to study the divergences at the boundary, for example, in strange space-times or weird space-time. We just could study a surface in the interior of the space-time who get inside of this surface, a black hole or something that you want to study, right? Matter distribution or whatever, energy distribution. In particular, we use this method to study three-dimensional black hole mass, and we have we taken a action of quadratic gravity. We take this action and we get this solution. We have the Lipschitz three-dimensional black hole. We compute this capital P tensor for this with this, we have this expression. We compute with this given this capital P tensor, we could get the boundary term, because obviously, okay, we have to. I need the last slice. Okay, we have to compute this nether potential, but also we need to compute all this boundary term, and that's the reason that we obtain the boundary term, right? In the last slide, there is a omega letter, but in this case, boundary term is a capital Pi symbol. The nerve potential is, okay, boundary term is given this capital P is in this wave, and nerve potential is in this wave. We choose a specific temporal killing for this Lipschitz black hole, and this is the temporal killing. We have the boundary terms explicitly. If we substitute the explicit form of P and use the killing vector, we have the boundary term, the nerve potential. The perturbation metric is necessary. We get all these things together, and we obtain the quasi-local quantity, quasi-local energy, in particular the mass of this black hole. And this is the mass of Lipschitz, the three-dimensional Lipschitz black hole, in terms of the this horizon, black hole horizon, right? Events horizon of this black hole. Okay, in conclusion, we have as a conclusion, we have the ADM method needs hyperbolic globality. We have flat asymptotic space. Obviously, it's pretty particular. It's not the most general space times. Okay, we use the ADT method. This ADT method needs a solution for vacuum equations. Perturbation vanishes at spatial infinity. And killing vectors, and obviously it's not general. It's not more general. It's not the most general method to study different gravitational space-times, and we need a quasi-local method. And in the quasi-local method, we need a general theory of covariant gravity, killing vectors, codimensional at two surface and parameterized path, but obviously we study a generic method. And this is it. Thank you so much.
Great, thank you, Steven. Thank you for the talk. Very nice. I will stop the recording now, and then we follow with the questions.